Hi, so in the previous video I was trying to prove the following using symmetry. So it was, we were given the following, so we know that if I have f of x minus tau and I apply Fourier transform, I get e to the minus I omega tau f hat of omega. And then the question was, the proposition was the following, that if you take e to the I tau x f of x, you multiply by e to the I tau x in the physical domain. Then if you apply Fourier transform, this what happened in the frequency domain, you get f hat of omega minus tau. And we gave a proof, using the definition. And then I was telling you that there's a proof using symmetry, and then I got stuck, okay? So let's give you the second proof, which is much, well, might seem a bit harder, but it's a useful proof. So proof, this is done, proof by symmetry. It's the following. So recall that f hat of x is f of minus x, okay? And that, so f hat of x goes to f of, so if you apply f hat, so if you start with f, you apply hat, f of x, you get f hat of omega, and if you apply hat again, you get f of minus x, okay? Now this is what we know, and I know that if I get f of x minus tau and I apply hat, I got f hat e to the minus I omega tau f hat of omega, okay? Now let's do the change. So if I take the function f of x minus tau, which really I called f tau of x, and I apply hat to this, I got e to the minus I omega tau f hat of omega. Now apply hat again, I should go back to my original function, which is f tau of minus x, okay? This is by the symmetry property. So if I apply hat twice, you go back to your function, but at minus x. So if I start with e to the I tau x times f of x, and I apply hat to this, and this is the question here. But I will use the following, okay? I will use that if I apply to e to the minus I omega tau f hat, I got f tau of minus x, okay? I know that if I take e to the I tau omega of f from here, okay? So let's start with the function f hat sub tau of omega, which by definition is f hat of omega minus tau, okay? Of x here, of x here. And then I apply hat to this. From the above property, what do I get? I got e to the minus I omega tau times f, I start with function f hat of omega, which is e to the minus I omega tau, but f hat at omega is nothing but f of minus omega. Okay. Now apply hat to this again, okay? Should go back to your original function, which is f hat of tau, but evaluated at minus x. which is nothing but f hat, well, f hat of minus x minus tau. Okay, so again, so I start with f hat tau, so I start with a function f hat of x minus tau. I apply Fourier transform. From this property, I should get the Fourier transform of whatever my function is, which is here f hat, so you get f hat hat of omega, times e to the minus I omega tau. And now now apply Fourier transform again. You should go back to your original function, but evaluate it at minus x, which is f hat evaluated at minus x minus tau. So this gives me that e to the minus I x tau f of minus x, if you apply hat to this, so I'm taking only this branch, and then if you apply hat to this again, you should get f hat at minus omega minus tau. So if I take g of x, which is e to the minus x ix minus tau f minus x, get this. Now take h of x to be g of minus x. What is g of minus x? It's e to the I tau x times f of x. Then what is h hat of omega by the dilation? Remember that if f goes to f hat, then f goes to f hat, then f of c x goes to 1 over omega f hat of omega over absolute value of c. So h hat of omega should go to, here c is minus 1 by dilation, so you should get 1 over absolute value of c, 1 over absolute value of minus 1 times g hat evaluated as omega over c. But I know that g hat of omega equal f hat of g hat of omega over minus 1, yes, which is 1, which is g hat of minus omega. But I know that g hat of omega is equal f hat of minus omega minus tau. So g hat evaluated at minus omega, which is e to the I x tau f of minus x all hat, is nothing but f of x all hat, it is this, which is h of x hat, is g hat of minus omega. G hat of omega is this, so this is f hat of omega minus tau. And this is the symmetry property. It will, you see, I proved it using symmetry. You can prove it explicitly, yes, but this is another proof. Now I know also, so you prove of differentiation property by symmetry. So if I want to prove this, then you know that if you take f of x and you apply hat, then you get f hat of omega, okay? So if you take f prime at x and you apply hat, you got I omega f hat of omega. Now if you apply the Fourier transform again, you should go back to f prime at minus x. Okay? So if you start with I x f hat of x and you apply, so if you start with f prime at omega, let's say you start with d f hat over d omega, okay, or if you take f, so the same thing here, hat prime and evaluated at x. Okay. Then if you do Fourier transform, you get I omega f hat of omega, which is nothing but I omega f of minus omega, and you apply Fourier transform to get, you should go back to your original function, which is f hat prime at minus x. Okay. So conclusion, if I start with I x f of minus x, if I start with this function, g of x is I x f of minus x, and I apply Fourier transform, I got f hat prime at minus omega, which is d f hat over d omega at minus omega. Okay. Now let's take h of x to be g of minus x, which is I minus x f of x, which is minus I x f of x. Now h hat of omega by dilation is 1 over absolute value of minus 1, this is c is minus 1, times g hat of omega over minus 1. And this is equal g hat of minus omega. But g hat of omega equal df hat over d omega evaluated at minus omega. So this means h hat of omega is equal df hat over d omega evaluated at omega. So this means the Fourier transfer of minus I x f of x, or there's just a few. If you apply the Fourier transform here, then you get what? You get f hat df hat over d omega. So x f of x, if you apply Fourier transform by linearity, get minus 1 over I, which is I df hat over d omega, which is the property. Okay, so I said, after finishing the video and trying to remembering what I meant in symmetry, I figured it out, and then this is what was missing from the previous lecture, that you can do both proof of differentiation, the second property of differentiation, and the multiplication by an exponential using the symmetry property, or you can do it explicitly. Okay, both work. You should know both, just so that you are used to this method.